This is Professor Rogers. This presentation is the second video in a two-part series on ordinary least squares regression, or OLS regression for short. We look at how the performance of the model is determined and where we find it on output in SPSS and PSPP. In regression analysis, the performance is sometimes referred to as the goodness of the fit of the model. We continue the example from the first part of the video series. In this example, state-level data was used to examine whether the poverty rate is associated with the log of the violent crime rate. Here is the output that we get in both SPSS and PSPP. Our problem is how well the line fits. The computer will calculate a line through a group of points, whether or not the line is descriptive of the relationship. We need to find a way to determine whether the line fits the points well, or whether the line has little explanatory power. To do this, we look at the model summary and ANOVA tables. We start with the sum of squares on the ANOVA table. ANOVA stands for the analysis of variance. To help understand the language of sums of squares, let's look at a hypothetical example. Let's suppose we have a distribution whose mean is 3. We represent this on a two-dimensional graph by putting 3 at every value of x, which results in the dashed line shown in this graph. One of the points in our distribution is 1, 1. Let's say that the regression line containing the predicted values runs through the point 1, 2, and that y hat, our predicted value, is 2. The total error in our model is called the total sums of squares. For each point, we calculate the distance between y and the mean of y and square it. Squaring the distance is not a new concept to us. It was first encountered when we learned about the standard deviation. We do this for every observation and sum it to create our estimate of the total amount of error. A portion of the error can be explained by using the regression line. The explained portion is the distance between y hat and the mean of y. This distance is also squared and summed across all points. It goes by many names: the regression sum of squares, the model sum of squares, or the explained sum of squares. The leftover, the distance between y and y hat, is also summed and squared. This number is what the model does not explain. It too goes by many names: the residual sum of squares, the error sum of squares, and the unexplained sum of squares. These numbers are reported in the first column of the ANOVA table and provide the basis for calculations in both the ANOVA and model summary tables. In the model summary table, the R-square is the measure of the goodness of fit. It is the ratio of the regression sum of squares to the total sum of squares. The result is a proportion ranging from 0 to 1. If we multiply R-square by 100, we can describe the number as the percent of the variance explained. The number summarizes the performance of the model, and it is the principal measure of the goodness of fit. R is the square root of R-square, which also happens to be the same as Pearson's R in the two-variable case. The adjusted R-square factors in the number of variables. The more variables we use, the more we can increase the R-square. However, an increase in the number of variables is not very efficient. The adjusted R-square statistic takes the number of variables into consideration when determining the goodness of fit. The model summary statistics do not account for statistical significance. The statistical significance of the model as a whole is found in the column on the far right of the ANOVA table. It is a value of 0.005, which is less than 0.05, meaning that the model is highly significant. The column in between the sum of squares and the significance level gives us the core numbers needed to make the calculation of significance. Let's start with the degrees of freedom. We are going to spread our error across 49 points. There are 50 points in the data set, but as we learned with the standard deviation, the error for the mean is 0, so all the error is spread over the remaining 49 points. This number of points over which we spread the error is the total degrees of freedom, which is n-1. The regression degrees of freedom is the number of variables, which in this case is 1. The residual degrees of freedom is the total degrees of freedom minus the regression degrees of freedom, which in this case is 49 minus 1, or 48. What is called the mean square or mean square error for each row is the sum of squares divided by the degrees of freedom. In this example, the regression mean square is 1.127 divided by 1, which gives us 1.127. The residual mean square is 6.266 divided by 48, which equals 0.131. F is the ratio of the regression mean square divided by the residual mean square. In this case, 1.127 divided by 0.131 is 8.637. The F distribution changes shape as the chi-square distribution does. The degrees of freedom are used in determining what the shape is. Since we need F and both degrees of freedom in the case of our example, we would say that F has a value of 8.637 with 1 and 48 degrees of freedom. We want 95% of the points to be to the left of this F value on the curve to establish significance at the 0.05 level. We have reached the end of this two-part presentation on simple OLS regression. Simple OLS regression is used when both dependent and independent variables are numeric. We learned that there is no single number that should be used to describe the relationship. We must look at all the output available to us. In the first video, we learned how to use beta and the standardized beta to understand the direction and magnitude of a relationship. The beta coefficients can be tested for their statistical significance. In this presentation, we learned that we can use the sum of squares to estimate the fit of the model, which can be described using either the R-squared or adjusted R-squared statistics. The fit of the model also has statistical significance.